Okay, so today I will talk about models for non-covalent interactions. It's needless to introduce non-covalent interactions. They are very important in chemistry, biology, material science, and one method that is widely considered at least qualitatively suitable for modeling non-covalent interactions was Møller-Plesset perturbation theory. For example, and specifically in terms of the cost, that was MP2, because anything higher order than MP2, such as MP3, was too expensive. The reason why it was considered at least qualitatively suitable was the fact that it shows the correct 1 over r to the power of 6 behavior of the dispersion energy. It is size extensive, and its convergence of the convergence of the Møller-Plesset series for dispersion energies, at least for small systems, is fast. And now there is a question: are these conditions actually sufficient to consider the whole series and the MP2 itself fundamentally adequate for the description of non-covalent interactions? For example, I show here a data set of large molecules, the L7 data set, and MP2 is showing errors that are greater than 100% in the binding energy of these complexes. And if we go one order higher, if we go to MP3, the things get a little bit better, but still for some of the complexes, the errors are more than 80% in the binding energies. In another recent paper of Vuckovic, who studied the applications of MP theory to non-covalent interactions, they found that for large systems, the MP series is actually diverging. And another thing that Vuckovic and co-workers found is that as a molecular complex increases its size, the relative MP2 binding energy also increases with the system size at the rate of approximately 0.1% per valence electron. And okay, this is not only the problem with MP2, but also methods that are based on MP2, such as those that I list here on the right, but also double hybrids, functional, and even double hybrids that are corrected by typical dispersion corrections, such as D3, D4 of Grimme. So all these methods can inherit these problems from MP2. And okay, so what I will do in these talks, I show here the average relative error for the L7 data set that I introduced. So average error for MP2 is about 60%. And in this talk, I will say how we made a correction for MP2 such that the error is greatly reduced to about 5%. And another thing, okay, so all that we did is within a pure electronic structure framework. So we didn't want to add atomic heuristic corrections such as D3 and D4. So everything we did was at the electronic level. Okay, in terms of the theoretical foundation for this work, what we did, we wanted to make a correction to MP2, and based on this Møller-Plesset adiabatic connection. Okay, so I give here the Hamiltonian that basically connects the Hartree-Fock state with a physical wave function. It is given by, okay, the usual kinetic energy, external potential. Here, the electron-electron repulsion is scaled by a coupling constant lambda, and we have these J and K operators for the Hartree-Fock. And if we denote psi lambda as a wave function that minimizes h lambda, then what happens at lambda equals 0? We have the usual single determinant, which is the Hartree-Fock state. And what we have at lambda equals 1 is the physical state. That is where J and K operators are being killed because we have 1 minus lambda in front of them. And in that way, we have the physical Hamiltonian. And then we can write the correlation energy in terms of this integral that goes from 0 to 1. And the underlying adiabatic connection integrand is going to be defined in this way that you can see on the right in terms of the psi lambda wave function. And what is the slope of this adiabatic integrand? That is given by twice the correlation and twice the second order, twice the MP2 correlation energy times lambda. So this is how basically MP2 approximates this adiabatic connection integrand. And what has been recently explored is like how this W lambda behaves as lambda is set to infinity, and it has been found that this lambda is a functional of the Hartree-Fock density. And what is important here to note that this whole adiabatic connection is not the same as the one that is used in DFT, and also this quantity W infinity is not the same one that is used in DFT. But again, okay, this quantity W infinity is what is important, that it has been found that it is more or less explicit functional of the Hartree-Fock density. Okay, but we know that if we want to compute this correlation energy by given by in this way, we need, this is more expensive than directly solving Schrodinger equations. So at least for it has no practical purpose, but this provides a powerful route for building approximations. So now I'm going to say, okay, how we use this formalism to get the approximations. And here I will first introduce our intermediate step, what they call here SPL, which allowed us, going back to the L7 data set, to reduce the error by roughly a factor of 2. This is still not satisfactory. I will go later how we went to here, but at least from the conceptual level, this was the more important step. Okay, so the whole idea in how this approximation was constructed, like to have a correction to MP2, was to have an interpolation along the adiabatic connection that I have introduced. And the whole idea was like to build this model for the AC integrand that does interpolation between this slope given by 2 times MP2 and this W infinity. And okay, to do this interpolation, we need some analytical formula, and we took this one, we borrowed it from DFT, and that was the form of Seidel, Perdue, and Levy, what I call here SPL. This is the analytical form. And then W infinity we have approximated with a simple integral over the Hartree-Fock density and exchange energy. So this is another quantity that is used. And another problem, another problem that in general, these models that depend non-linearly on the ingredients, they suffer from, they are not size consistent. However, we have showed relatively recently that this can be fixed basically at no cost with the size consistent, with the size consistency correction. And this correction is also one of the ingredients that I use here. Okay, so this correction dramatically decreases the errors. So for example, I show some around here dimers involving noble gases. And once this size consistency correction, SCC is turned on, basically the errors are dramatically reduced. Okay, so as I said, I want to build here a correction to MP2. So what I use in the end are this MP2 itself, an exchange that we already get by running an MP2 calculation. And what is on the top of that is this simple integral over the Hartree-Fock density and size consistency correction that also comes at no additional cost. And therefore, the overall construction basically requires no extra cost, because only this simple integral is calculated, which is fed into this first equation, and that is basically all we need. Okay, so again, before moving to results, I want to remind you that this was intermediate step. Basically, it included no empirical parameters, and I want to show how far we could go with that approach. Okay, so on the right-hand side, I show the results for the S66 data set. And we can see so our results are in black. These are the errors. And we can see that for dispersion interactions, it corrects MP2 quite a lot. Same for mixed complexes. But on the other hand, for hydrogen bond, it becomes worse than MP2. And another thing that we have built with this model for the adiabatic connection is the diagnostic tool for MP2. And we can ask a simple question: when MP2 is going to work? Okay, so MP2 approximates this adiabatic connection curve with a simple line. And in cases where this exact adiabatic connection integral, where the curve is quite linear, then we suppose that MP2 is going to do a good job. On the other hand, what is shown here on the right, when there is a significant curvature in the integrand, then we assume that MP2 is going to be a poor approximation for the correlation energy. And what we have built is this, what they call MAP, which is an MP2 accuracy predictor. Basically, it represents a dimensional measure for the adiabatic connection curvature, and it is given by this simple formula, where this quantity at the full coupling strength we extract from our model. So basically, when MAP is equal to 0, then the adiabatic connection curve is perfectly linear, and this in turn means that MP2 is going to do really a good job. Okay, so I show here some results. On the x-axis, I show this MAP, which is again MP2 accuracy predictor, and on the y-axis I show the errors. So again, as this map is small, that in those cases MP2 is supposed to give good results. And as MP2 increases, then the errors are, as map increases, the MP2 errors are supposed to increase as well. So what we have here at low map values are typical hydrogen bonded complexes where MP2 is doing really a good job with the relative error in binding energy just about 3%. On the other hand, when this map is increasing, in that case, the exact curve is going to be quite, will have quite pronounced curvature, and MP2 becomes a poor approximation, and basically here it becomes all useless because its relative error in binding energy, this pi-pi stacking complex, benzene dimer, it's about 70%. And another thing what we looked at, we wanted to see how this map, what is this map value as a function of dispersion electrostatics ratio from that we calculate from SEP. And we found as the higher dispersion electrostatic ratio, we have the larger these map values. This in turn means more pronounced adiabatic connection curve curvature. And this in turn means that MP2 is less accurate. In other words, like the more we have dispersion in a complex, MP2 will do a worse job. Okay, so now I want to go, from this intermediate step to our improved results that we got with SPL2, because we saw with this SPL, we could get some success, again, reducing the error by a factor of 2, but this is still not satisfactory because we won't be competitive with D3 corrected functionals. So we need another step to get closer to this accuracy. Okay, so what we have found was one simple reason why SPL form, the interpolation form that we have used to build our model, it didn't contain enough flexibility. And a simple step to go further was like just add one extra term. But in this way, we have 6 parameters that we have to obtain from somewhere, and 3 of those parameters are same as the previous form, which is SPL, and they have been obtained by these exact constraints. However, we found, we are exhausting our possibilities, what we can do with fully non-empirical approach. So we decided, let's see what happens if the remaining parameters we train on the S22 data set, and this is how we obtain those. Okay, so I'll show here results. Okay, so what is shown here on the x-axis is the error of MP2, and on the y-axis I show you how much our models correct that error. So if all these data points lie on this y=x line, then our model would be perfect. And this is the previous model, SPL, the orange one. Okay, so it corrects well as the error of MP2 is small, but when the error of MP2 becomes large, it does not correct enough. And this is also another problem with SPL, is that, in most of the cases, MP2 overbinds complexes, but there are few cases where MP2 underbinds complexes. And in those, our previous model was correcting MP2 in a wrong direction. And these are the results with the new model. It displays a good corrective behavior of MP2 even when the errors of MP2 are large, but also when MP2 underbinds, it corrects it in the right direction as opposed to our previous model. And so I will show you now some results. I will start with the krypton dimer. So the black one is the exact one, and then the green one is the one that obtained with the newest model, with this SPL2. MP2 overbinds, and we are also better than B3lib-D3 corrected. And typical double hybrids such as B2p-lib, if you don't add any dispersion correction to it, to it, it basically are not able to describe dispersion interactions. And now this is a question, if one looks at the form of SPL2, it can be considered a double hybrid because, okay, it contains exact exchange, it contains MP2 correlation, but also some quantities that are defined as an integral over the Hartree-Fock densities. However, I'd like to point out that there are two key differences between SPL2 and standard double hybrids. The first one is that our model used the full exact exchange and the full MP2 correlation. And in this way, does not rely on the error cancellation between these quantities and their semi-local counterparts. And another point here is that all our models, they do not require any dispersion or van der Waals correction to accurately describe non-covalent interactions. And these are the key two differences of why the model that we developed is different from double hybrids. Okay, so now I go back to the L7 data set showing the results for individual complexes. Okay, so we are doing better than B2P-lip and B3-lip corrected by D3. MP2 is, as shown before, is doing very badly. And our previous model was doing halfway between MP2 and our present model. Okay, so I mentioned also before pi-pi stacking complexes. Here, this is benzene pyridine dimer. We are also doing a good job. Here, B3-lip D3 is also highly accurate. And in this case, we are on pair with D3 corrected functionals. On the other hand, this is an acetamide dimer where B3-lip D3 is not so accurate, but still in this case, we get improved results over both D3 and MP2. Okay, so here, these are the results obtained with other data sets. We are systematically always improving over MP2 and our previous model. Probably the most striking is this L7 data set where the mean absolute error is reduced by roughly factor of 10, and it's still by roughly a factor of 2 better than B3-lip D3. Another, for example, for S22 and for S66, B3-lip is doing just slightly, marginally better. But for charge transfer complexes, we are doing roughly by 3 times better than B3-lip corrected by D3. And now I will spend a little bit time talking about these charge transfer complexes. So I show here the binding curve for the fluorine ammonia complex. And the black one is the exact one. I show you here MP2 is the blue one, B2P-lip is the purple one, and B3-lip is the brown one. Okay, and this is what happens when you add D3 correction on the top of these functionals. It basically worsens the results. And okay, this has in another work we have found why is that. It's because D3 worsens the results here because of the so-called density-driven error in charge transfer complexes, and D3 is actually has not the right physics to fix that problem, and in turn it worsens the results. On the other hand, our model is doing well for these charge transfer complexes, which explains also why our error for CT7 dataset is much lower than D3 corrected hybrids or double hybrids. Okay, so I like to summarize this part of the talk. So what we did was we built a model that is highly accurate for non-covalent interactions, and it basically at no cost corrects MP2. What is a very important element of this is that it's not based on error cancellation. So we do not introduce semi-local exchange that replaces part of the exact exchange. Also, all we do here is without any dispersion corrections added on the top of electronic structure calculations, and this in turn fixes the problems where these corrections fail, such as in that charge transfer complexity that I showed you. Okay, so this is what's done, and what still needs to be done is everything we did so far was with MP2, but okay, we want to lower the cost. For example, we can use local MP2, and also there are another cheaper approximations to MP2, such as UV12, that has been recently developed by Fred Memby, which we can use to replace the MP2 part in our model. Okay, there is also room for accuracy improvement. In a way, we optimize our model was quite crude, quite primitive. So we just use S22 data sets, but this means that we still have not exhausted possibilities for improving the accuracy of our models. And in terms of implementation, I think it can be easily implemented in any code that contains MP2. All you need, basically, this SPL2 model is based on MP2 plus simple integral over the Hartree-Fock density, and this is all you need, and therefore it can be easily implemented in any code that contains MP2. And okay, I'll just briefly mention here some other work that I have done on non-covalent interactions that can be of interest to you. Okay, this particular work in this paper was about how errors in geometry translate into errors for binding energies. It provides a fresh look into benchmarking methods for non-covalent interactions. And another point was, okay, so we revised the D3 correction. So we have found that in cases where the DFT error is very bad, then D3 correction worsens the results. I showed previously charge transfer complexes, but this is also characteristic for water clusters, and we have found a way how these density-driven errors can be reduced before the D3 correction is added. So here you can see the results. Okay, if one takes PB for these water clusters, and if you just add D3 correction on the top of it, the results are much worse. But if you include the density correction first and then add D3 on the top of that, then you get much better results. And okay, here I would like to thank people who contributed to this work, and also funding agencies. And I'd like to thank you for your attention.
Thank you, Stefan. Right. Very good. Thank you very much. So let's see, we're about 45. So I think if you have a question, you can just present yourself, unmute yourself and ask the question. Oh, yeah, last time maybe I was not clear. When I ask you if you have a question to raise your hand, I mean, don't sit like this behind your camera, but there's a button for those that who do not know to actually raise your hand, because somebody pointed out to me that people were raising their hand and I was not giving them, I didn't let them ask their question because I didn't see. So Mathieu gives the example. Sorry, Giovanni.
I saw Rex raising his hand, but not in the chat.
Yeah, I just found out how to do it. Yes. Could we go back to the first results that you showed us for the SPL2, which I think were for 6 or 7 different sets of molecules, including the S22, on which you trained the new parameters.
Okay, just give me one. Okay, I will reshare my screen.
Yes, you can leave the slides up there.
Okay. I believe you mean this.
Yeah, exactly. Yeah.
Okay.
So on the left there, could you explain to us which of these points come from the S22 set?
Okay. So I cannot tell that. So this is I think that these points are roughly somewhere here, like between, because MP2 does not its errors are not greater than 5 kilocal per mole.
Okay, so that's nice. So
Yeah.
the right-hand part of the curve, which is very impressive.
Yeah, so this
for
is
non-S22 molecules. Great.
Yeah, so for example, these data points are one that pertain to larger complexes. They're not present in S22. So
Mathieu?
my guess is that S22 is data points that pertain to it is in this region.
Right.
I had 2 questions. Maybe the first one is just something I missed. Is there a basis for this functional form that you use with a constant plus constant over square root of stuff? Does that come from some analytic model for adiabatic connection? Or is it just something that looks like your curve as a function of lambda with a limit, or what? Okay,
so this should be this. Okay, no,
right.
This is an analytical. So there in the literature, there have been several forms like this proposed, and this was based on the features of how W behaves as a function of lambda. So it should decrease as lambda increases.
So it has the right asymptotes, but it's not, there isn't a physical basis for the actual shape as a 1 over square root and so on.
Yeah, it has the right asymptotes, so it's correct in the 2 limits up to the second order. But how you interpolate it's in a way arbitrary. So, we tested different forms, and okay, we empirically found that this was the one that worked best.
And based on this, do you have a feeling for why it's so much better when you fit with 2 of these functions rather than 1? Because in the end, your asymptotes will be the same, right? You've got to compensate it between the 2 sets of A and A1, A2, and so in principle you could fold them together. It feels like you need a slightly more complex functional form. And again, is there a physical basis for what it should look like?
I think that by fitting this, we get some, in a way, we get some information for the orders that we do not use. So this is just my feeling. So how we go from MP2 to the large coupling limit, I think this is kind of some information we extract from fitting. And another point is that this, okay, so give me 1 second.
I'll give you 5.
Okay, I'm trying to find the slide. Okay, I have, so basically also this first model, SPL, it was always convex. And this is fine because MP2 in most of the cases overbinds. But there are few cases where there are a few cases where MP2 underbinds, and in that case, the exact curve is concave. And with this new form where we added one,
or potentially even just some of its derivatives might be changing sign. Even if the whole thing stays concave, it might have, yeah.
Yes,
Mhm.
yes. So, but at least with another extra term, we gave it more flexibility.
Sure.
So it can
That
be
goes
more
without saying, but then you can start adding, reams of parameters. I had a final question about whether you can carry any of this over to solids, where people are using D3 shamelessly, and it looks like it's really hard to beat based on what you're showing, but you have done it. Is there some way you could add this on top of COSEX self or RPA self energy or something like that?
Yes, I think we thought a little bit of that. So now there are people like who implemented MP2 for solids. So I don't know. For example, double high. Also, I saw a recent paper like double hybrid functionals, like XYG3 or something. They're applied to solids. So if these are applied to solids, I don't see a reason why this cannot be applied, but we need to go there and see if we are still accurate for solids as we are for molecules.
Okay, thanks a lot.
Stefan, you got a question?
Yeah, it's more a remark than a question, and it pertains a bit to Mathieu's question before. At least if you do the DFT adiabatic connection, you have another possibility at infinity, at lambda going to infinity, not just take W infinity, but also the derivative at infinity. So, well, yeah, I mean, that's what we did some ages ago. And I'm sure you looked into that as well.
Yes, we looked into that as well. And so indeed, like there is a difference between lambda infinity between DFT and this Hartree-Fock. So DFT people like Michael Seidel and my previous supervisor, Paola Gori-Giorgi, they explored it like for decades almost. But this is something new. And but actually also the next leading order up to the third was recently discovered. So indeed we can try then to simplify and try to feed into these models and see if there is any improvement in accuracy if we bring those into the game.
Rex has another question.
Can I ask about the van der Waals coefficients? You mentioned that MP2 already gives a 1/r to the sixth dependence. Presumably not with the right coefficient. Is that right?
Yeah.
And does SPL2 improve the coefficient?
We have not looked at the coefficients explicitly, so we looked at those curves, but we believe that but probably this information can be extracted from these curves. So indeed, we can look at that. So we focus here on binding energies, but indeed, like I suppose that we are doing also better for the coefficients, but we should check that.
Stefan, you had another question, though you didn't lower your hand, I guess. Okay.
Sorry, I have to lower my hand. Yes, sorry.
No, it's okay. Just a minute. I was just wondering the W infinity. Where does it? Can you say something how it is derived? So it's not an exact relation, but approximate. And do you know what is the error?
Okay, so this is how we modeled it. This is so-called PC model, point plus.
It's small. Could you represent it in full screen?
Okay.
Or get rid of the format panel on the right.
Okay. Now, can you see it?
Yes, thank you.
Okay. Yeah.
Okay, so this is approximated. This is approximated in terms of the density, but we have found that even the exact form of this W infinity within the MP adiabatic connection is not too expensive. So what we can try is to model it with the exact one. So this should be applicable at least to smaller molecules. And okay, so this is GEA approximation. And another point was, okay, we want to make a real GGA model for that. So this is another thing that we are doing at the moment.
And so now you use Hartree-Fock self-energy. Could you use another self-energy?
But here, you mean, but here Hartree-Fock is our reference point. So what we want is to build the correlation on the top of the Hartree-Fock energy. And the reason why we evaluate this functional on the Hartree-Fock density is because it has been, it has been found that this large coupling limit is a functional of the Hartree-Fock density. So that's the reason why we have used this.
Okay, and that's an exact result.
Yes, that's an exact result. And that when you go to lambda infinity, the Hartree-Fock density survives. So that's but then in terms of the form, how we approximated, that was an approximation.
Okay, Stefan has another question, but maybe first Lucia, she hasn't asked the question yet, and then Stefan.
Okay, it's just to this. You said it's a functional. You said earlier it's an explicit functional of the Hartree-Fock density. Actually, it's more or less an explicit functional of
more or less an explicit. Okay, so what I meant by that is basically to. Okay, so in that case, when lambda goes to infinity within this Hartree-Fock adiabatic connection, the wave function collapses, so into Dirac wave functions, and basically electrons are sitting at certain points, and those points are determined minimize the positions within the Hartree potential. So basically what survives is the Hartree potential. So you take the Hartree potential and you find where electrons sit. So in that way, it's not explicit functional of the Hartree-Fock density, but it's not very complicated. So
okay,
that's.
Thank you.
Stefan, you had another question?
No, another comment. It's about this W infinity. I think, I mean, the functional form is exactly like this point charge plus continuum model.
Yes.
Mike Seidel developed like in the 90s, I think it was even.
Yes.
So it has exactly the DFT form. I don't know about the parameter values you use, but I suppose they're probably also very similar. No? I mean, like these prefactors A and B, I believe you call them.
Yes. So we have found, okay, so this PC model is an approximation to DFT. And, but we have found the inequality between the DFT large coupling limit and the Hartree-Fock and this MP1. And we have found that this Hartree-Fock one is well approximated if you have this PC model minus twice the exchange. So that was the rationale why we used the PC model, which is in the first place, as you say, designed for DFT, why we used it here. So there is some inequality that connects the DFT one and the MP one.
Okay. Are there any further questions? Did you have another question or hand it up? Okay, no problem. if there are no other questions, so maybe we can stop here. So thank you, Stefan, for this nice talk. And so if you want, you can join us then on the Wonder platform. Let's see how that works. It's pretty intuitive, so I don't need to explain it. I think let's see how it goes. Okay, thanks to everybody for joining and for the discussion. Okay.
Okay, thanks a lot.
So see you in a minute, or see you next month. Okay.
Bye.
Thanks, Stefan. Bye bye.
Bye-bye.